today is another day where we're realistically just going to look at the in-class assignment and then get into our lab. So today's in-class assignment is specifically related to doing nodal and or mesh analysis in the frequency domain. Realistically, I'm only asking you for this to write a KCL equation for one particular node, and then write a KCL equation for a supernode, and then define Ix in terms of the nodal voltages. But we're going to go through the full procedure of applying nodal analysis here. And then I'll leave you guys to do problem 2 by yourself, which is a similar thing, just using the mesh relationships. But I want to make sure that you know how to use MathCAD in order to solve systems of complex equations, because that is going to be required of you on some of your homework assignments and stuff like that. So for this first problem, I've already given you the nodal voltages and defined ground and all of that kind of stuff for you. I'm going to go ahead and still identify our nodes just so they're a little bit easier to see exactly what's going on. So this guy right here will be node 1. This guy is node 3. Here is our node 4. This is our node 2. Here is node 5. Let's see. This will be 6. And then lastly at ground down here. So we have 6 different nodes plus our referent, and we also have 2 different controlling variables. So that means we're going to wind up needing 8 equations in order to solve this system. Okay. So from our nodal analysis steps, we've identified our nodes, we've labeled our nodes. So now we would be at defining our controlling variables in terms of our nodal voltages. So let's start with our relationship for Vx. So anybody have any thoughts on how we might express Vx in terms of our nodal voltages? Yeah, V2 minus V1, that's it. So that one is fairly straightforward. Ix can be a little bit more difficult. So realistically, there are 2 different ways that we can express our current Ix in terms of our nodal voltages. We can say that this current flowing in plus this current flowing in plus this current flowing in sum together to make Ix. Or we could also say that this current flowing out plus this current flowing out also have to be Ix, because we know that Ix is defined as the current flowing from left to right through this branch. So this current right here is also Ix, right? So I'm going to actually just bother doing this using both expressions just for the heck of it. But when I set it up into my system solver, I'm only going to use one of those 2 expressions because I don't want or need any redundant information in my system of equations. Okay. So using the pink arrows, we would have V2 minus V5 over 7 ohms. Plus V4 minus V5 over minus J5 ohms plus 0 minus V5 over 4 ohms is equal to 0. Or we could say that Ix is going to be equal to the current flowing up through that current source. So that's 2 angle 0 degrees amps plus the current flowing down, which is simply V6 over J6 ohms. Oh, sorry, there shouldn't be an equal 0 there. It's my fault. So before we move on from here, does anybody have any questions, comments, or concerns about our controlling variable relationships? All right. So at this point, we would then, if we were looking at a DC circuit, we would then write any KCL equations that we would need for our supernodes, okay? So this particular circuit has 2 supernodes because there are 2 voltage sources. So we have this supernode right here. And we also have this supernode right here. Okay. Neither of these supernodes contain ground, so that means that we have to write a KCL equation for both of them. Okay. So I'm going to start with supernode 1, 3. So that will be this current flowing out of node 1 plus these 2 currents flowing out of node 3 sum together to make 0. The current flowing out of node 1 is just going to be V1 minus V4 over minus J2 ohms. The current flowing to the right through the 1 ohm resistor is going to be V3 minus V4 over 1 ohms. And lastly, the current flowing down through the J3 ohm impedance is simply going to be V3 over J3 ohms. Set this equal to 0. And now over here to the right, I'm going to do KCL at supernode 5, 6. Okay. So that's going to mean that we're adding together the currents that are flowing out of node 5, as well as the currents that are flowing out of node 6. We already realistically have all of these currents written down for when we defined Ix. The only thing we really need to do is make sure that the direction of all of those currents where we defined Ix at node 5 essentially are in the opposite direction, because all of those currents originally we counted them as flowing in, and now we're counting them as flowing out. So that's going to look like V5 minus V2 over 7 ohms plus V5 minus V4 over minus J5 ohms plus V5 minus 0 over 4 ohms. So those are our 3 currents in pink. And now we're going to have our 2 currents in orange. So that'll be 2 angle 0 degrees amps plus V6 over J6 ohms. Set that equal to 0. So anybody have any questions about our KCL at our supernode equations, or why we needed to write KCL equations at those supernodes? All right. Yes.
It's just more about basic. Why do you write the number after the J instead of before? I get that J is not as a number when that is a variable,
Mhm.
but my brain pulls up my variable rules to it and put the 3 before the J.
So literally every electrical engineering textbook expresses numbers in this form where the J is first because it is indicating that that is the beginning of the imaginary part. So I have simply followed suit because it's been done this way for about 100 years at this point. Yeah. I do find it annoying for what it's worth that your calculators can't put in numbers like that. So what I usually do to wrap my brain around it is I just put a 1I and then the thing that I'm interested in so that it treats that 1I as the imaginary operator J. All right, so now we're just left with our remaining KCL equations. So we've got 1, 2, 3, 4 equations already. So I believe we're looking for 4 more relationships, right? So that should be KCL at oh, oh my goodness. I forgot the voltage relationships. That's where the other two are missing. Sorry, I skipped a step there. I only saw 2 more nodes and I started to worry about what I had forgotten. And then I realized what it was. So realistically, we should have done these voltage relationships before we did our KCL at our supernode. So I apologize for forgetting those. So every time we have a voltage source when we're doing nodal analysis, we will have a voltage relationship equation, okay? So I'm going to start with that 12 angle 0 degrees voltage source. So 12 angle 0 degrees volts is going to be equal to what combination of nodal voltages? V1 minus V3, thank you. And then we have this 3Ix dependent voltage source. And how is that related to our nodal voltages? V5 minus V6, thank you. Okay. Now we're left with our remaining KCL equations, which is the first one we're going to have is KCL at node 2. Okay. So that's simply going to be this current plus this current. So that'll look like V2 minus V5 over 7. And then I'll have minus 2 angle 0 degrees amps is equal to 0. Because the current we're interested in is flowing down to the current source and the direction the current source is up. So we have to flip the sign. Nothing different than what we've been doing, excuse me. The last thing we need to do is then write our KCL equation at node 4. So that'll be this current up, this current to the left, this current down, and this current to the right, like so. So our first one is going to be V4 minus V1 over minus J2. The current flowing to the left is V4 minus V3 over 1 ohms. The current flowing down is negative 2 Vx. And lastly, the current flowing to the right is V4 minus V5 over minus J5. And set this equal to 0. All right, so all I'm going to do over the next minute or two is plug all of these relationships into MathCAD. So because we're solving a system of equations, we are going to have to use a solve block, much like we did when we were learning how to do just basic nodal and mesh for DC circuits. Okay. Now, this isn't explicitly required, but it is a habit of mine, so I'm going to continue to do it. Whenever I'm solving a system using complex numbers, I start out by declaring my variables essentially as complex numbers as well. So I'm going to have my first variable is going to be V1, and I'm going to say that it is open parentheses 1 angle 0 degrees. So I want to show you something here really quickly. If we go under this operators tab and we go down to engineering, this is where we get our angle operator. Notice that it tells us the keyboard shortcut for the angle operator is Control-Shift-P. So I'm going to press Control-Shift-P instead of going into this menu over and over again because I am lazy, okay? Another thing that I want to point out, if we go over here to the left and we look at the degree symbol, there is not a keyboard shortcut to express our angle in degrees. So I'm going to show you a workaround for that in just a second. Okay. So I've got my 1, Control-Shift-P gives me my angle operator. Here's my 0. So right now, this is in radians. I'm just going to type DEG, and the computer actually knows to count that as an angle expressed in degrees. So it's a little less convenient than just having a dedicated keyboard shortcut, but it's way more convenient than having to go and pull it out of that drop-down menu over and over again. So this is kind of the best that we have an option with. Outside of these parentheses, I am now going to multiply by my unit of volts, okay? And I'm going to repeat this process for the remaining nodal voltages. So here's V2, 1 angle 0 degrees, volts. V3, 1, oops, angle 0 degrees, volts. V4, 1 angle 0 degrees, volts. Oops, I did not mean to do that square root. And now I'm going to do it for, was it Vx and Ix? Okay. All right, so I've declared all 8 of my variables. Just to remind you guys, that particular equal sign is the shift colon, and it's essentially just declaring your variable and giving it some initial value to start with when it does its iterative solving process. Now in the constraint region of our solve block is where we're going to type in our equations, right? So my first equation was for the controlling variable Vx. So that would be Vx is control equals to my nodal voltage V2 minus my nodal voltage V1. Now for Ix, I'm going to choose the easier of the 2 equations to type in. Once again, we can call it laziness or efficiency, whatever floats your boat, it's all the same to me. So that's going to look like 2 angle 0 degrees, oops, amps plus V6 over, and now I have to do J6 ohms, okay? So I want to show you guys something really quickly here. So I'm going to type in 6J, oops, and then I'm going to multiply by an ohm, where to get that ohm symbol, that it was capital W and then control G to convert it into Greek, just like it was when we were doing nodal and mesh at the beginning of class. I have to put that multiplication between the J and the capital omega, otherwise it treats it. So let me show you guys what happens. If I just do J and then capital omega, notice that the J is now in italics, which means it's treating it as J omega is a variable instead of it is the imaginary operator J multiplied by the unit of ohms, okay? So that multiplication between the J and the capital omega is incredibly important. Bless you. Also looks like I did the wrong equal sign here, so that should be control equal. There we go. Fix that. Now we're going to do our voltage relationship equations. I'm going to do it in the order I should have done things. So that'll be 12 angle 0 degrees volts is control equal to V1 minus V3. Then I'm going to have 3Ix. So that is a current controlled voltage source. So what are the units on that 3 for a current controlled voltage source? So the output is voltage, so voltage needs to be in the numerator, so volts per amp. And this is V5 minus V6. And now I'm getting down into the KCL at my supernode equations. So KCL at supernode 1, 3 was going to look like V1 minus V4 divided by minus 2J times omega plus 3 minus V4 divided by 1 ohm plus V3 divided by 3J times capital omega is control equal to 0. Now I'm going to do my KCL at supernode 5, 6. So that's going to look like V5 minus V2 over 7 ohms plus V5 minus V4 divided by minus 5J times an ohm plus V5 divided by 4 ohms plus 2 angle 0 degrees, goodness, multiplied by an amp plus V6 over 6J times an ohm is equal to 0. And then lastly, I have my 2 regular KCL equations. So that'll be KCL at node 2, which looks like V2 minus V5 over 7 ohms minus 2 angle 0 degrees amps is control equal to 0. And then now I'm doing KCL at node V4. So that'll be V4 minus V1 over minus 2J times an ohm plus V4 minus V3 over 1 ohm minus 2Vx. So this is a voltage controlled current source. So what should the units on this guy be? Amps per volt. And then lastly, I've got V4 minus V5 divided by minus 5J times capital omega is equal to 0. And now I need to give myself room to put in my matrix, where this is going to be an 8x1 matrix. Here's V1, V2, V3, V4, V5, V6, VX, IX, same variables in the same order. And it spit out my answer in rectangular form. So let me show you guys how to fix that. If we go into the math formatting tab here, in this results area, there's a drop-down menu that has the title complex values. So MathCAD can return complex numbers either in rectangular form with I as the imaginary operator, rectangular form with J as the imaginary operator, polar form with our angle expressed in pi radians, polar form with our angle expressed in radians, and lastly, polar form with our angle expressed in degrees. So for the intents and purposes of this class, it's always going to be rectangular with our angle, excuse me, with J as the imaginary operator, or polar form with our angle expressed in degrees. I'm going to choose this one, and these are our results. Okay. And if my memory serves me correctly, these are correct. At least Vx and Ix I know for sure are correct. And if those two are correct, then everything else is probably correct as well, because how else would it have worked out that way? So realistically, this is exactly the same thing that you were doing with nodal analysis earlier on in the class. It's just now you're using complex numbers. So I just wanted to make sure that you knew how to put complex numbers into MathCAD, how to format your answer to give you the result in the form that you want, since web work can be so finicky and all of that kind of good stuff. And I can't force you to use units, but I would definitely encourage you to do so because it's way easier to make MathCAD spit out the answer in the units you're looking for, as defined by the problem statements and all of that kind of stuff in web work, than it is to suffer through trying to manipulate things after the fact because there's so much bookkeeping involved that it just gets gross.